Alright, this is Jeff Coles, and we're covering the last regular lecture on solution of nonlinear systems. First, I'll just recap previous lecture looking at linear systems, as that will become important as we evaluate the response of the nonlinear system near the critical points. The general solution looks something like this. X of t equals k1 e to the alpha t cos beta t plus k2 e to the alpha t sine beta t. This is a system of two equations. We also have the response of the y variable, k3 e to the alpha t sine beta t plus k4 e to the alpha t cos beta t. Now there's a bunch of parameters here, these constants, k1, k2, k3, and k4. These are established by the eigenvectors and the initial conditions, but they are not time dependent in our autonomous linear system. So again, these are the resulting equations, solution from system of equations that looks like this: a, b, c, d, x, y. So this is a linear system of coupled equations. We solved one identically, and then we saw, or analytically, and then we started looking at what happens, the system response based on the eigenvalues. Here, in this case, this is for a general eigenvalue of the form lambda equals alpha plus I beta. These are complex eigenvalues. They have a real part, they have a complex part, and again, I is the square root of -1. And in this particular case, because it's linked to real biology, its purpose is only mathematical. And ultimately, due to the fact that in this system of two equations, you will have two eigenvalues, they will be complex conjugates of each other. So the first one will look like this, lambda 1 equals alpha plus I beta. And the second one will look like this, alpha minus I beta. And the eigenvectors will do the same. And when you start multiplying out everything all together as a big mess, the imaginary parts will cancel out, and you have a totally real solution. That's the only possibility of this form. But due to Euler's equation, the imaginary part ends up here in these harmonics. Here the imaginary part beta, and the real part alpha ends up here in these exponentials. And that's a key thing. So those are both components of the eigenvalues. They're in very different form in the solution. If we look at the general function f of t, some function f of t equals e to the alpha t cos t, call it cos beta t. We look at solution or function of this form. We have, which is essentially our solution above is written as functions of this form, essentially an exponential times our harmonic. We get different kinds of solutions. If alpha is greater than 0 and beta is not 0, you get solutions of this form, where you have this part here is just going to oscillate with a period t equals 2 pi over beta, and just it will oscillate for eternity, but it's being modulated by this time-dependent amplitude here. If alpha is greater than 0, then that will grow with time. The larger alpha is, the faster it will grow. So you have a growing amplitude, and the solution will essentially look like this. So here's time, and the peaks here are bounded by exponential functions. So this function up here can be described as e to the alpha t, and this one could be negative e to the alpha t. And that's the harmonic lives inside this growing envelope. If alpha is less than 0, you have the opposite effect. The envelope converges in like this, and the actual time-dependent function is going to shrink with time. This will continue to decay to 0. So you have a growing oscillator, a decaying oscillator. If alpha is 0, then the function will oscillate just as a regular sine or cosine waves as a harmonic. The envelope will be constant. And then we have the other cases that we looked at when you have no harmonic component where beta is 0. And these parameters here defined all the different possible types of solutions. So again, this system of equations here has one critical point when x equals 0 and y equals 0. And we wanted to evaluate what is the nature of the solution near that critical point of the linear system. And that came down to being independent of the initial conditions and entirely dependent on the eigenvalues. And we had a little table we came up with essentially where we looked at various solution types. For example, this one. So here's the origin of the phase plane. This is x and y. The one critical point is here. And if the solution were given an initial condition here and were to simply progress in phase space around and around in closed circles, this was the case where beta was non-zero and alpha was 0, basically. And in our time series, would look something like this, where this might be x and y can be out of phase and have a different amplitude, but they both will oscillate a constant amplitude to infinity. And each closed loop represents one period of oscillation of the system, and x and y have the same period, and that's equal to 2 pi over beta in seconds, or in our time units, whatever they may be. This was a neutral center. And we went through all the different possibilities, real or negative and positive, real parts in combination with a non-zero imaginary part, a real and positive, real positive eigenvalues with no imaginary part, etc. We came up with a little table that looked like this: real part, imaginary, what the type was, and the stability. So for the case where both real parts, alpha 1 and alpha 2, are greater than 0, so you had two eigenvalues, purely real, both positive, that was an unstable situation. It's going to grow with time. I just put that in the wrong column here, 1 second. The type of that was a spiral, a nodal source, nodal source. That was unstable. And then we had a case where we had the eigenvalues were both real but of opposite signs. So if you multiply them, you get something less than 0. One's negative, one's positive. No imaginary part, purely real. This was a saddle point. It was unstable. I'll just put a U here for unstable. We had both eigenvalues were real and negative. Again, real, so no imaginary part. This was a nodal sink. So the population time series does not have any oscillation to it. It just simply decays to 0 as an exponential. This is stable. And then we started looking at ones that had non-zero imaginary parts, where the real part, there's only one real part in that case, was greater than 0. The imaginary part, beta, was non-zero, doesn't matter the sign. This was a spiral source. It is unstable because of those alphas. We'll switch the sign of alpha, less than 0. Beta again not equal to 0. This is a spiral sink. Stable. Everything's going to decay back to that critical point. And then we had alpha equals 0. Beta not 0. So no real part, only imaginary, purely imaginary eigenvalues. And this was that neutral center. Which will put a question mark. I'm not sure. That depends on what we're looking at, how we're going to define that. Because in this definition of stability, if we perturb it from the critical point, we have two cases. It returns to the critical point, or it proceeds very far from the critical point. In this point, with this neutral center, if you perturb it an infinitesimal amount, it goes to an orbit which is only infinitesimally far from the critical point. So it can't be deemed stable or unstable, but I see most people calling that stable. Now we're going to look at a nonlinear system. This was the predator-prey equations. The rate of change of x, we wrote in its classic form, the rate of change of x dot, was equal to ax minus bxy. And we have dy dot was negative cy plus dxy. So we have four terms, four parameters. This term is a growth term. This term is a mortality term for the predator. So this is a predator. And this is the prey. And these are the coupling terms. It's a negative term in the prey equation and a positive term in the predator equation. And depending upon how you discretize this in terms of energy or mass, B and D can be different parameters related to the efficiency of metabolism. And then first part of this analysis, we went through null lines and things like that, but a key thing that we left out was looking at the critical points. What are the critical points of this system? We can solve this for two critical points, and they are, let me just scroll back here. Two critical points. One was x and y equal to 0. That satisfies x dot equals 0 and y dot equals 0. So critical point is where both equations are in equilibrium. Both systems are in equilibrium, meaning that our time rate of change are 0. So at this point, the origin of phase space, state space. And we also have a second point, xy is equal to c over d comma a over b. So in this equation here, we can pull y out of the equation, and we have a negative c plus dx. If x is equal to c over d, negative c plus dx is 0, and therefore y dot is equal to 0. With this equation, if we have y equals a over b, then we have x dot equals 0. So this is the second point, and this is a potential coexistence point in phase space. Here's phase space, creature x, creature y. Here's the origin. Neither of them exist. Here's this magical point c over d, a over b. Both creatures exist. What is the nature of the stability of these 2 points? Well, we can do that by linearizing this system of equations. And we found the equivalent linear system could be written in this form, where we have u primed, v primed equals the Jacobian. Partial f, partial x, partial f, partial y, partial g, partial x, partial g, partial y, u, and v. Here, u is the difference between x, our variable x. Let me write this more properly. U of t is the difference between x and this critical point, minus x critical. The critical point at x, value of x, so either 0 for this critical point here, or c over d for this critical point here. So this is a perturbation from that critical point. in the x direction. The perturbation from the critical point in the y direction, or y direction is y of t minus the y critical value, which depends on which critical point we're looking at. So the solution to this perturbation can be written as a linearized system where we have as our matrix, our constant matrix, this Jacobian here. F is the right-hand side, so for a general nonlinear system, we have x dot equals f of x comma y, and we have y dot equals g of x comma y. So let's go ahead again and write our predator-prey equations just so we have them at the ready. We have x dot equals ax minus bxy, and we have y dot equals negative cy plus dxy. So let's form this Jacobian. Partial f partial x, which I've written in shorthand as f sub x, is equal to a, derivative of this with respect to x is a, minus derivative of this with respect to x is minus by. We have fy, the derivative of this function here with respect to y. The first term is 0, the second term is negative bx. We have gx, derivative of this nonlinear function with respect to x. The derivative of the first term is 0, second term is dy, and gy. Derivative of this with respect to y is negative c plus dx. Put this together as our system. We have u primed, v primed, so the rate of change of these perturbations around the critical point is going to be, let's see, a minus by, negative bx, dy, negative c plus dx, u, v. So this is written in the form z dot equals a z. It is a linear system. The nature of A depends on which critical point we're at. If we're at x comma y equals 0 comma 0, the first one, we plug that in to the system of equations here, and our matrix looks like this. Everything's basically 0 except for the a and the minus c, and our system of equations u prime v prime is equal to a 0 0 minus c uv. And this is a diagonal matrix A. The eigenvalues of a diagonal matrix are the diagonal entries, A and minus C. So we have two eigenvalues, both real. Lambda 1 equals A. Lambda 2 equals minus C. One is positive, one is negative, both real. Therefore, the critical point x comma y equals 0 comma 0, is a saddle point. The second critical point, x naught, y naught equal c over d a over b. If we go back, plug that into our Jacobian. So we let y be a over b, and we let x be c over d. This term goes to 0, this term goes to 0. This ends up being negative bc over d, and y equals a over b. This is dA over b. And our system looks like this, u dot v dot, new system of linear equations because we're at a different critical point, 0, negative bc over d, dA over b, 0, uv, and the eigenvalues of this are going to be, remember, eigenvalues of our matrix A come from solving for the determinant of A minus lambda I, where I is the identity matrix. We set that equal to 0. So we have the determinant of negative lambda, negative bc over d, dA over b, negative lambda equals 0. The determinant is this times this minus this times this. So we have lambda squared plus, now you see the d's are going to cancel out, these b's are going to cancel out, plus AC equals 0. The solution of that is lambda squared equals minus AC. Take the square root of both sides. We have lambda equals the square root of negative AC plus or minus. And the square root of minus 1 we can pull out of here. That's I. So they get lambda equals plus minus IAC, where I equals square root of minus 1. These are purely imaginary eigenvalues. One is positive, one is negative. So then the question is, does this make sense? This is a neutral center, right? We come back to our solution that we examined in class using null lines and actually plotting the solution. It looks something like this, where this was C over D, A over B. The solution form these closed ellipses. Tend to propagate in this manner, X, Y. Here's one critical point. Here's the other critical point. Now this one, the origin, was a saddle point. Saddle points have one axis along which they are stable and all others are unstable. In this case, we have this along the predator axis, x equals 0, which is a x null line. We have a stable system. If you perturb it by adding predators, it will return to the origin. If you perturb the prey by adding prey, it will grow indefinitely. There's no density dependence in these equations. And if you perturb the system in any manner around the origin with combinations of x and y, it will go into these population cycles. Therefore, this is the axis along which the system is stable. All other axes is unstable. So this really truly is a saddle point. And this point right here, the coexistence point, is a neutral point. So it is stable in the sense that we aren't going to lose our population. And the system will form harmonic closed loops around that critical point. And the amplitude of the loops are going to depend on the initial conditions. The population is initialized here versus here. You're going to have two different system responses. Out here, you're going to have a system response with larger amplitude. Again, the mean value is still going to be the same, but it's going to be a larger amplitude. Same period. Here, you have smaller amplitude, same period. And we discussed that as being a bit unrealistic. That's something that will be addressed, could be addressed in your project. That may be one of the project options you want to look at. So let me stop here and then we'll talk a bit about competing species in the second segment.